We want to show this primitivity criterion. Let's start with this direction first. So we assume that E mu is primitive, and we show that then we can write this product E mu Q E mu as a multiple of E mu, no matter what the Q. Okay. Let's consider the left ideal generated by E mu and give it a name. Let's call it L. And now for, say, any Q in our group algebra, we define a linear map. Let's call it capital Q from the group algebra to the group algebra, and we define it like this. We say Q times R for any group algebra element R is R E mu Q E mu. So it's right multiplication with this product here. That's our linear map. Now consider this here. QSR. What's that? That's SR multiplied by E mu Q E mu. But R times E mu Q E mu, that's just capital Q times R. So we copy the S, and then we have QR. And now we see that QS is equal to SQ with all these R's, with any R here on the right. Okay, so this is true. This is true for all S and R in the group algebra. But if it's true for all S and R in the group algebra, it's also true, let's say, for all R in L. It's just a subset of the group algebra, and for all S in G, that's some other subset. Okay, why is this interesting? If this R is in L, then the whole equation here takes place on L. We multiply something that's in L from the left, so we stay in L. This means the S here, if the S is in the group, then the multiplication with S from the left is just the representation of the group which is carried by L. Okay? So, but now this representation, it commutes with the Q. So let's write this down. So this means Q commutes with the representation of G carried by L. Okay, now let's use that E mu is primitive. We want to prove this here from the left to the right. So if E mu is primitive, that's the same as saying that L is minimal. And minimal L means it's an irreducible invariant subspace, so this representation here is really an irrep. But if this representation is an irrep, then Schur tells us that now the Q is a multiple of the identity. The identity on L. Okay, so what was Q? Was defined up here. So Q was right multiplication with E mu Q E mu. What's the identity on L? That's right multiplication with e mu. So we know that this thing is a multiple, let's say lambda q, some complex number, times e mu. Right multiplication with e mu q. E mu is the same as right multiplication with the multiple of e mu. So we showed the first part of this. The left-hand side implies the right-hand side. What about the other direction? Let's create some space here. So now this way. Now we can assume that e mu q e mu is a multiple of e mu, and then we have to show that now e mu is primitive. What we're going to do is we're going to assume that e mu is not primitive, and this will lead to a contradiction. Okay. So we assume that e mu can be written as e1 plus e2, and neither e1 nor e2 is 0, and products are 0. So e1, e2 is 0, and e2, e1 is 0, and each of these idempotents. So this means if this was true, then it would not be primitive. And now we have to show that this is a contradiction to this equation here. Okay. How can we do this? Let's look at e mu, e1, e mu. So since we said e mu is e1 plus e2, we have this triple product here. And now all the mixed terms are 0 because of this. And then we have a e1 cubed, but e1 cubed is just e1, since e1 squared is e1. On the other hand, we know that there exists some number lambda. Let's just call it lambda. We need no index here. Some number lambda such that e mu, e1, e mu is just lambda e mu. So now we've used this here. Okay, and if we compare these two, then we see that now lambda e mu is equal to e1, but e1 is equal to e1 squared. And since e1 is equal to lambda e mu, we can also write this is lambda squared e mu squared, but e mu is idempotent, so we have lambda squared e mu. And this means that lambda is equal to lambda squared. Okay. But lambda equal to lambda squared, that's the same as lambda is 0 or lambda is 1. What happens in these two cases? If lambda is 0, then e1 is 0. That's a contradiction. So that's a contradiction to e1 being non-zero. What if lambda is 1? Then e mu is equal to e1, but that's a contradiction to e2 being non-zero. And then we're done.